Assalamualaikum and hi everyone, I'm Mariam. Welcome back. This is my second video of my respiratory system lecture. If you haven't seen the first one, please click on the link in the description below. So today we're going to look at the lung expansion and recoil, lung volumes and capacities, and then finally we're going to look at the pulmonary and non-pulmonary function test. Now we're going to look at the muscles of respiration. So as you can see here, we have muscles that are involved in inspiration and muscles that are involved in exhalation. So now if you look at right over here, we have the diaphragm, right? Diaphragm. So diaphragm is the main muscle for respiration. So that's the primary, we call it primary. And also the external intercostal muscle. External intercostal muscles are also the muscles that are involved primarily in the respiration. And as for the rest of the muscles, these are all accessory muscles. So what it means by that is that the mainly when you are at rest, breathing at rest, where you're not doing any activities, you're only using your primary muscles, which are the diaphragm and the external intercostal muscles. And if, let's say, you're doing hardcore activities that involves you a lot of movement, and therefore you'll be needing a lot more muscles for you to inspire and also for exhalation, and you'll be using just more than the usual muscles, more than the primary muscles during your respiration. All right, now we're looking at the movements that are involved in expiration and inspiration. So firstly, I've talked about the primary muscles that are involved. So the first one is diaphragm. So we have your diaphragm in the first one, and I've said here downward and upward movement of a diaphragm. Now diaphragm naturally it's a curve, it's like a dome, right? So when it contracts, it goes downward. So when diaphragm contracts, again, let me remind you, it goes downwards. Contraction of diaphragm will lead to an increase in volume, all right, to an increase in thoracic volume or the lung volume. So increase in volume, and if you remember in my first lecture, I've talked about volume and pressure. So as volume increases, you have decreased pressure, right? So as volume increases, pressure decreases, right? So if diaphragm contracts and it moves downward, it increases the volume, and therefore pressure will be reduced, right? Now the second thing here, I've put elevation and depression of the ribs. Okay, so sorry for that. I can't draw straight lines, right? So the muscles that are involved here, particularly, like I said again in the earlier slides, the external intercostal muscles, right? External intercostal muscles are the primary muscles, and the contraction of these muscles will cause an increase in the thoracic volume as well, right? Increase in the lung cavity, right? So increase in the volume will cause decrease in the pressure. So increase in volume will cause decrease in the pressure. Right, so this is again in this slide, I'm showing you the contraction and expansion of the thoracic cage. So basically, what I've explained earlier, this one is also explaining it, right? So in expiration, the diaphragm relaxes and moves up, right? Rib cage is pulled downward, and the chest wall and abdominal structures compress the lungs. So this is during expiration. So I'm going to put there in blue, right? During expiration, the diaphragm relaxes and moves up. So remember I said that the diaphragm is naturally in dome shape, right? Now, so when it relaxes, it goes back to its original shape, which is the dome shape, right? So this one, and the chest will, be relaxing too. Chest wall, muscles of the chest wall will be relaxing too, and therefore reducing the pressure, reducing the volume. Reducing the volume, right? So if you have something that compresses, it reduce the volume. So if you have volume being reduced, you are increasing the pressure, right? So when pressure increases, therefore it will be pushing the air out. So increase in pressure, and there is a decrease in the pressure outside, right? So the inside is an increase and outside is the same. So if there is a difference, remember again I talk about gas law, right? And the gases moves from a higher concentration to a lower concentration. So since the pressure inside is now increased, so you have the air moving out, right? So the air will move out. I'm going to use a different color for the air. So the air is now, for example, so the air moves out. So this is the air, right? So air moves out because of the increase in pressure building up inside the thoracic cavity. Now, in inspiration, so I'm going to use a different color for inspiration. In inspiration, right, so in inspiration, diaphragm contracts and moves down. Rib cage is pulled upward and expanded. So here, let's say, imagine this is the diaphragm. So when diaphragm contracts, it flattens out, right? So if you compare with the expiration phase, you have the diaphragm curled back to its original position, which is the dome shape. And once it's contract, it is, it flattens out. So it's not as curved as in the expiration phase. It now is flattened. So, and the abdominal chest wall now expanded, and it goes upward, right? So expanded, it goes this way and it goes up, right? So upward and expanded. So therefore you have a total increase in the volume of the thoracic cage. So once the volume is increased, you have a decrease. You have a decrease in pressure, right? Pressure decrease. In here you have increase in volume. So I'm going to put here volume, right? This is for volume, and this is for pressure. Okay, so right, so pressure decreases and volume increases first, and therefore pressure decreases because of that. And because of this pressure decrease, and the pressure outside is the same, but you have a decrease in the pressure inside, right? And so the outside air will tend to come in, and this happens during inspiration, right? So in inspiration, you have air coming in, right? Okay, so air will come in. Right, now let's talk about the pressures that are involved in ventilation, right? And then previously I've talked about the gas law that says that gases basically move from a higher concentration area to a lower concentration area, right? That's basic. And then as long as there's pressure gradient, the air will move from a higher pressure area to a lower pressure area, which also means a higher concentration of that particular gas, to an area where there's low concentration of that particular gas. Now in in our ventilation, and we have to bear in mind that there are two important pressures that are involved in ventilation. So the first one I've highlighted here is the alveolar pressure. So alveolar pressure is the pressure inside the alveoli, right? And then there's transpulmonary pressure. So the transpulmonary pressure is the pressure difference between the alveolar pressure and the pleural pressure. And if you look back in my first video, and if you remember, I've talked about the pleural pressure, where I've mentioned that the lung is covered by has got double layer of covering, right? So the first layer is the visceral layer, and then there's parietal visceral pleura and parietal pleura, and in between those layers you have the fluid that flows in between those layers, right? And in between those layers there's a pressure, and we call that the pleural pressure, right? So this pleural pressure is always negative. And the good thing about it being negative is that it causes air to easily move in and easily move out. And because of the difference in the pressure, right? Pressure difference, because it's always negative, it will always have that pressure difference, and we want that pressure difference. So because air basically moves when there's pressure difference in pressure, and when there's pressure gradient, right? So we want to have that pressure gradient all the time so that the air moves easily in and out, and so the pleural pressure is the one that's providing that. And finally, here I've put in air flows into the alveoli when the atmospheric pressure is greater than the alveolar pressure. So I put here ATM, which means the atmospheric pressure. So the pressure outside, whenever it's bigger or it's higher than the pressure inside, you have air coming in. Again, like I said, gases move from a high concentration to a lower concentration, a higher pressure to a lower pressure. So whenever the outside is greater, then you have the outside moving in, and if the inside is greater, then you have the air inside the lung moving out, right? So that's basically that. So the pleural pressure changes here during inspiration is when the chest expands, it decreases the pleural pressure. So when the what it's saying here is that the pleural pressure, although it's in a closed area, is in between, and it's not directly affected by the expansion or the reduce in the volume of the chest, but there is a slight decrease in the pressure, right? So if there is a decrease in the pleural pressure, a slight decrease in pressure will tremendously changes the transpulmonary pressure, and this will help in the movement of air, right? So the alveolar pressure then decreases below atmospheric pressure and air flows into the lung. So this is what happened during inspiration. So what it's trying to say here is that the transpulmonary pressure difference also help the movement and the decrease in the pressure, the overall pressure of the alveolar, and this will further help in the movement of air into your lung, right? Right, in this diagram you can see that the air, this is the how it looks like at the end of expiration, we're going to start off with at the end of expiration, right? So at the end of expiration, you can see that there is no air movement because the pressure inside and the pressure outside has equalized. So at the end of the expiration, you can see that the diaphragm is being in its natural dome shape, and the chest wall is also not contracted, right? So it is in its natural position, and the air concentration has equalized with the outside, and therefore there is no net movement, of air. Okay, so in this diagram, I'm showing you, so once the expiration has ended, right, and there's equivalence of air concentration inside and outside. So now you want to start breathing, you want to start to inspire, right? So at the start of inspiration, you have contraction. First, you have to talk about the muscles, right? So you have first the contraction of the muscles. So remember, we've talked about the primary muscles that are involved in respiration. So the diaphragm is the first one, and then you have the external intercostal muscles. So diaphragm and the external intercostal muscles contracts. So when these muscles contract, when diaphragm contracts, it flattens out. So originally we saw that the diaphragm is in its dome shape, and now it's slowly losing its dome shape and is slowly flattening out. And this as you can see, the muscle wall, the external intercostal muscles are also contracting, and there are, when they contract, you have the thorax expanding. So when you have the thorax expanding, you are increasing the volume of the thoracic cavity. And once this cavity is increased, you have the pressure decrease. The pressure inside decrease, it will cause the pressure outside higher, right? So basically when the pressure inside is decreased lower than the outside, so the air from the outside will start flowing into your lung. And that's how you inspire. That's how it is at the start of inspiration. So now you're looking at the during inspiration. So remember just now there were the increase in the volume of the thoracic cavity, right? Volume increase, pressure decrease, so air starts flowing in. Air only moves when there's pressure gradient, right? And now the gradient is that the air outside is in a higher concentration compared to the inside, so the air will move from outside to the inside. So this is during inspiration. So now you can see that at the end of inspiration, the diaphragm is flat, and the thoracic cavity is at its most expanded volume, right? Because of the contraction of the external intercostal muscles, and also the contraction of the diaphragm. And you can see that the air moves until there is no more pressure gradient. There is no more difference in the pressure inside, and there is no and the outside. So when there is no difference in the pressure inside and outside, the air movement is now zero. So the net air movement is now zero. This is the end of the inspiration. Now, after the end of the inspiration, now you wanna expire, right? So you have now all the carbon dioxide, and you have less oxygen, and you wanna remove the carbon dioxide. So then you wanna start to expire. So the first step in the expiration process is that the muscles will first have to move, right? So the diaphragm now relaxes. And also, along with that, you have the external intercostal muscles are also relaxing. So now when diaphragm relaxes, you can see that the arrow here is showing you that the diaphragm goes upward when it relaxes, and it's curving back to its dome shape. And also, along with that, the external intercostal muscles, as they relax, you have the movement of your chest downwards, right? So it moves inward, inward, and downward, right? So as they relaxes. So now this one will cause a reduce in volume, right? So when volume reduces, you have increase in increase in the pressure, right? So now the pressure inside is higher than the pressure outside. So we'll see what happens next, right? So next what happened is that you can see that because of the movement of the muscle, because of the relaxation of the muscles, so particularly the diaphragm and the external intercostal muscles here. So the relaxation of both muscles causing the reduce in the volume and the thoracic cavity, causing the increase in pressure. And you can see that now, arrow here, it shows that the air is now moving out, because the air inside is now greater than the air outside, than the pressure outside, right? So greater concentration, a greater pressure. So the movement is from the outside, the movement is from the inside to the outside now. So this is basically what happened during expiration, right? Right here you can see the pressure changes during breathing, and this is related to the lung volume. So you can see here now, I'm gonna use let's see, red. Okay, here you can see the reduction in the volume of the lung. So as the lung volume reduces, you can see that there is an increase in pressure of the pleural, right? The pleural pressure increases. And remember that the pleural pressure plays an important role in respiration, in that it is directly related to the volume changes of the lung. So now you see the reduction in the volume of the lung causes an increase in the pressure, and this pleural pressure increase um, will help in the pushing out of air during expiration. So when exhalation occurs, the air moves out. So this is what happened. So now, if the lung volume increases, you can see that now the lung volume increases. Let's look at this area here. Lung volume increases, and you can see down here that there's a decrease in the pressure, right? The pleural pressure decreases. And if you look at the graph, the increase in the lung, and you can see that the reduction in the pressure is equivalent to the increase in the lung volume, right? And the important thing about this pleural pressure is that because of its because it is directly related to the lung volume, it helps in the alteration of the alveolar pressure, right? As you can see here, the alveolar pressure and the pleural pressure difference. Look at the gradient, it's much greater during inspiration compared to during expiration. What does that mean? It means that during inspiration you want a greater pressure gradient, and this one will help with the movement of air. Remember that we talk about gas law, and if the pressure gradient is increased, you have a greater rate of movement, and the diffusion rate will be, will be increased, right? So because of the great difference between the concentration, great difference between the pressure, so the air will move faster. And looking at the expiration phase, you have, and if you compare it with the inspiration phase, the difference in the pressure here and here, it's slightly smaller compared to during inspiration. And this small pressure difference, meaning it's not that great, the air moving out, it moves out, but it's not that great unless you're forcing yourself to exhale air out, right? Then you're putting more pressure, so this one then will be increased, right? The flow pressure will be increased then when you forcefully exhale. Okay, so this is generally what this graph here is showing you. So here let's look at the factors affecting ventilation. So now we know that the volumes of the lung plays a very important role in alteration of the pressure, right? So we know, and the pressure correlates with ventilation, and you need the difference in the pressure for you to either inspire or expire. So lung volume and capacities is the first one, and then you have the pressure, and we talk about the pressure difference. So the more difference in the pressure, you have a lot more movement. And number 3 is the compliance and elasticity. So this is related to the lung. We're going to look at later the compliance of lung and what does it mean by elasticity of the lung. And then number 4, we're going to look at the surface tension and surfactant. And then finally number 5, the resistance. And what is resistance that we're talking about here? Right, so we've talked about lung volumes and capacities before, but I did not explain you in detail. And what I've introduced to you before in the first video is the tidal volume. And if you remember, tidal volume is the volume of air that that are involved in respiration in a normal person who is not involved in any activities, right? So this is volumes breathing at rest. So you have the tidal volume here. And then so let's talk about the rest of the volumes that are involved. So we're going to look at first the inspiratory reserve volume. So this one is or you can just put it IR V. So inspiratory reserve volume is the volume of air that when you inspire with effort, right? At your last exhalation, and then you top it up with extra inspiration with force, with greater effort, and up to the point where it's at its maximum level. So you call that the inspiratory reserve volume. So that volume that you inspire deeply, inspire at most, is the inspiratory reserve volume. So how we calculate that is that if you calculate the volume of air that when you inspire at the maximum minus the tidal volume, you get the extra volume is the IRV, right? The inspiratory reserve volume. Now let's look at the expiratory reserve volume. So this one can also be written as ERV. I'm just gonna put here ERV. Yeah. Okay. So we have here expiratory reserve volume. So this ERV refers to your last after your last exhalation, and you exhale on top it up with forced exhalation with all the accessory muscles that we've talked earlier, right? So to your maximum. So if you have that volume of air when you exhale till you cannot exhale anymore, so you get that volume and you minus the tidal volume, you get that volume of air that you call ERV, because that extra volume that you exhale, the extra volume of air that you exhale is the expiratory reserve volume here. Okay, right. So now let's look at residual volume. So you can also write this down with just RV. So residual volume denotes the volume of air that is left behind, and that are that are usually I mean, there's that air that cannot be exhaled out no matter how hard you try to exhale out, right? So there's always this air that stays inside your lung, and this is what we call as residual volume. And remember, we've talked earlier in the first video, we've talked about the dead space and the air that's inside. So the residual volume are air in the dead space, and the rest of the air that are not being expired out. So it's the dead space are included. The volume in the dead space, volume of air inside the dead space are also involved in this residual volume, right? And then now there's this capacity. Now you see the word capacities here. So we have lung volumes and capacities, and we've talked all about the 4 lung volumes. We have the tidal volume, and we have the inspiratory reserve volume, or IRV, and we have the expiratory reserve volume, ERV, and finally we have the residual volume. Now let's look at capacities. I'm going to use a different color for lung capacities. All right, now let's look at lung capacity. So lung capacities is the additional value from the volumes, lung volume. So if you add on, if you can see the arrows in the graph here, right? If you add on inspiratory reserve volume with tidal volume, you will be able to get inspiratory capacity. So this one is equivalent to, inspiratory capacity is equivalent to IRV, IRV plus TV, where that's tidal volume, right? So inspiratory reserve volume plus tidal volume is equivalent to inspiratory capacity. And then if you add on the ERV, ERV with RV, RV is the residual volume. So if you add ERV and RV, you will get that functional residual capacity, FRC. And if you add on IRV, TV, and ERV, you get that vital capacity. So it's IRV plus TV plus, really bad at this, and plus ERV. Yeah, and you got the vital capacity. And lastly, if you add all of this IRV here, TV here, ERV here, and also RV here, you get total lung capacity. So all the capacities are actually lung volumes being added up. Here's another graph that shows you the lung volume change and the pressure changes based on the lung volume change. So you can see that here, let me show you that if the lung volume change, let's say we take 1 point here, okay, take 1 point here. So you can see that the lung volume change here, but the changes in, and then if let's say the volume increases up to this level, you can see that the difference in the pleural pressure from here, from this point to, from the lower point to the upper point here, is not much of a change, right? As slightly slight change, but not much. So this is the situation if the lung is filled with saline, if the lung is filled with fluid. So the efficiency of the volume changes reduces because of its filled with fluid. And if let's say normally the lung is filled with air, right? So if let's say the lung volume change from this point, right, this point here, to again to this point here. So if the lung volume change from here to here, you can see that the difference in the pressure from this point to this point, the curve is slightly more compared to this one. The curve is more. There is more changes here compared to this one here, right? The changes here is more change compared to this one. So what I'm saying here is that the efficiency of fluid is less. So compared to the if you have air inside, the pleural pressure changes is very much improved compared to when the lung is filled with fluid. So what would happen if the parietal pleura was punctured but the lung was not damaged? So if you look at this diagram, this picture is showing a hole here. So I'm gonna use some color. Right, there's a hole here. So the wall is being punctured, and this is, remember I've talked about again, this is the parietal pleura, right? This layer here is the parietal pleura, and the inside layer is the visceral pleura. And if the parietal pleura is being punctured, you've got air from the outside coming in, right? Air coming in from the outside, so air would rush into the intrapleural space, and the lung would collapse. So as the air, because of the pressure, remember I've talked about the pressure inside these pleural cavity, it's always negative compared to the outside, compared to the atmospheric pressure. So when there's a puncture, the atmospheric pressure will come in, and they will come in till the pressure inside and the outside is in equilibrium, right? Till it is equal in concentration, right? So, and that as they do that, as they come in and enter the cavity inside here, they will cause lung to shrink. How do they do that? They push, since more and more air comes in, then they push the lung to one side, and you have this condition, we call it as pneumothorax, right? Yes, this is a condition we call as pneumothorax. Right, so in this slide you can see the pneumothorax, or the collapsed lung that we've talked about earlier, and you can see in the X-ray this the region of collapsed lung. You can see right over here that there's an area where there's empty, it's empty, and lung supposed to be there, but it's been pushed in. right? Because of the puncture, and then the pressure inside and outside is different, and so air will come in, and it will come in till the air inside and outside is equilibrium. Right, now so now let's talk about lung compliance. So compliance is the magnitude of the change in volume produced by a given change in pressure. The greater the lung compliance, the easier it is to expand the lung at any given change in transpulmonary pressure. What it's saying here is that the greater the lung compliance, then the better it is to expand. So compliance is about change in volume given by a change in pressure. So if you have if the lung is in a high compliance condition, then the lung can easily expand, right? As you change the pressure, as you change the volume, and then change the pressure, and the lung will respond to it easily, compared to a lung that has less compliance. Low compliance lung will not it is harder for the lung to expand in response to the change in volume. That's what it means. And then there is elasticity of the lung. So elasticity is all about the ability of the lung to recoil, to oppose stretching. So here you can see the explanation I've put. The tendency of an elastic structure to oppose stretching. That's what elasticity means. And the lungs naturally have a tendency to collapse because of its elasticity, and they are held open by the negative pleural pressure. And this is the other important value why the pressure in the pleural cavity is kept as negative, right? So it holds the lung open. The chest will naturally expand, but it is also held by the negative pleural pressure. So the elasticity of the lung can be imagined as a rubber band. So if you have a rubber band, and if you pull that rubber band will have the tendency to want to come back to its original shape, and that is what we call as elasticity. So the rubber band has higher elasticity compared to if you have a string. Now a string is, if you have a string and then you have an elastic band, the string has no elasticity compared to the rubber band, right? So the rubber band has got elasticity, but the string has got no elasticity. So that's what it means here. Since we were talking about the elasticity of the lungs, so now we're going to look at the characteristic of lung compliance are determined by two elastic forces, right? So the first one is the elasticity of the lung itself, and then secondly is the forces, elastic forces, and this is produced by the surface tension of fluid that lines the inside walls of the alveoli, so the inside wall of the lung. So here we're talking about surface tension, and then water molecules characteristic is that they are always attracted to one another, and they will try as best as possible to be to be near to each other, to be near to each other, and they won't allow, and if they are near each other, they don't allow things to pass through between them easily, right? So that causes surface tension. So if you look at this diagram that I have here on the left side, you can see that this is one water molecule, all right, and it has it has tension from all from all four directions, right? Up, above, and left and right. And if you put another water molecule next to it, so it will immediately connect to one another. It will immediately pulls one another close, right? And so in water, you can see that all these water molecules are attached very tightly to each other. And then as for the water molecules at the surface, for example, this is the surface, right? And you have water molecules too at the surface, right? You have this one, and you have this two, and you have this three water molecules at the surface. And you can see that the one next to each other is pulling each other close. Okay, but there's no water molecules above here. There's no water molecule here, and there's no water molecule here as well. So because there's no water molecule, the net force that is being produced by each of these water molecules on the surface here, particularly all these three water molecules, is downwards. You have a net force pulling it downwards because of this, because there's no water molecules above. So this only happens at the surface because there are no other water molecules, right? So, and they try as best as they can to stick togetherness, right? So you have a total force of going down because of this, and that force is tight, and then the water molecules tend to hold tightly to one another, especially at the interface here, especially at the surface here. So that's why if you look at the photo on the right, you have this insect, and because of the surface tension that is being produced by these water molecules at the surface, these insects can't walk on the surface of the water molecules. This is another picture showing water molecules, and then so this is if you look at this picture, it tells you that these are water molecules in water, and you don't see it at the surface, so they're just floating freely, right? Because they're in water, and there's so many other water molecules around them, and because there's no there's no area where there's no water molecules, so it's free and easy, and everyone's and everybody's just around you, so the force is not that strong here. So if you look back in my previous slide, where there's surface and there's that surface tension, because there's no water molecules above and only below, therefore the force tends to pull it downwards, and then you have that surface tension. So again, this picture has got water molecules in the water. If you have a lot of water molecules inside here, and then there's no more water molecules outside here, right? So because of that, there is a surface tension here because of the force pulling downwards. The force pulls downward, and we've talked about this before, that since there's no water molecules above, the water molecules that are around each other, they try to maintain as best as possible to stick to each other tightly, and because there's no water molecule above, right? So this force here is greater than the one inside here. Yeah, so compared to the water molecules inside, they are they are water molecules everywhere, so they don't have that net force of only one way, right? So it's not that tension here. So the tension here is less than if you compare to the tension in the water molecules at the surface. So again, we're talking about the surface tension here in this picture as well. Again, as you can see, that all the water molecules that are inside, they don't have that force, that one direction force. I mean, they are, it's less pressure, less tension compared to the water molecules at the edge. The one that is at the edge is the one has got no water molecules in front of them, and so they tend to tightly hold onto one another. One water molecules tend to holding tight to the one next to it because there's no water molecules in front, right? So and this tight force is the one that creates the surface tension here, and then it's tighter at this area, at this surface. And if you have like remember we talked about that insect that can walk on water, and this is the surface tension that that builds up because of the water molecules, and so it becomes hard enough for and for that insect to be able to walk on it, right? So yeah, and we've talked about the alveolar cells in my first video. I've mentioned that there are two types of alveolar cells. There's type 1 that's mainly flat, and they are the one that make up this alveoli. And then you also have type 2 alveolar cells, and these cells um, are spread out, and they are in these in lung as well. And type 2 alveolar cells are the ones that are secreting surfactants. And surfactant is a complex mixture of phospholipids, proteins, and ions, and it has got a surface, it has got a part which likes water and the other part which do not like water, and we're going to look at that later in another slide. Right, so a little bit on surfactants in neonates. What you have to know is that in babies, in premature babies, they often have alveoli with diameters less than a quarter that of an adult. And we've talked about volumes and pressure. And in Boyle's law, it states that in my first video we've talked about Boyle's law, right? So Boyle's law states that if there is a higher volume, then you have less pressure, and if you have a low volume, you have a higher pressure. And so if you relate that with neonates which have alveoli with a diameters less than a quarter, it means that the volume of this of the lungs in neonates, in premature babies, is very, very small compared to that of an adult, which means that the pressure inside the babies is greater than the pressure inside adult lungs. And to top it up, the surfactant of this naturally, surfactant is being secreted into the alveoli during 6 to 7 months of gestation. It means pregnancy. So only at the 6 to 7 months of pregnancy that you have surfactant. So the lungs of premature babies are more likely to collapse because there is no surfactants being produced. And the condition of respiratory distress syndrome of newborn is the concern in premature babies. So this is surfactant. So I've told you that surfactant has got a part that loves water and the other part that hates water. So this part that loves water is the hydrophilic part, and the part that hates water is the hydrophobic part. So you have the tail hydrophobic and the head hydrophilic. So if you have an oil here and then water outside, So you have the head on the outside and the tail pointing inside because of the two different characteristic of the surfactant. And so according to the law of Laplace, if two bubbles have the same surface tension, the smaller bubble will have higher pressure. And looking at A, you have one large bubble and you have one small bubble. And if you use the formula, P, pressure is equivalent to 2T, so 2 times T divided by R. So R is radius, T is tension. So pressure is equivalent to 2 times tension here is 3. So this P here in the large bubble, 2 times the tension is 3 divided by 2. 2 is the radius, right? So you've got the pressure is 3. And looking at the small bubble, you have total pressure of 6. And how do we do that? We calculate P is equivalent to 2T. So T here is 3 and divided by R. So radius here is 1 and you've got the answer here is 6. So you've got the pressure of 6, and if you compare that with the large bubble, you have a small pressure, and in the smaller bubble you have high pressure. So that is according to the law of Laplace, where you have if there is the same surface tension, but because of the volume is bigger, you have a lower pressure. And because the volume in the small bubble is smaller, you have a higher pressure, right? So in B, if let's say surfactant is used to reduce the surface tension, so in a bigger bubbles, you don't have to reduce the surface tension much because the surface tension is, I mean, in bigger bubbles, you don't have to reduce a lot of surface tension because naturally in bubbles with large volume, and we've talked about large volume having low pressure, right? So what you want is to direct the small volume bubbles, because small volume bubbles tend to have higher pressure compared to the large bubbles, right? So you want to reduce that surface tension, and that pressure builds up in a smaller bubble compared to the large bubbles. So here, if you look in, and if you use the same formula, 2T, so the P here in the large bubble in B, 2 times T, so the surface tension in the big bubble is 2, so 2 times 2 divided by the radius is 2, and you've got a pressure of 2. And if you have the smaller bubble and you look at and using the same formula, 2T, so it greatly reduces the surface tension in the smaller bubble compared to the bigger bubble. So you have 2 times 1, right? 2T is 2, so 2 times 1 and divide by the radius, so the radius is 1. You've got the answer 2. So you've got the pressure is also 2. You have the same pressure, although the bubble is very small compared to the bubble on the left. Right, so this is peak expiratory flow test, and this is one of the easiest tests to look at your lung ability. And you just need to have your peak flow meter, and that's it, and you plot yourself a graph. And if you have, I mean, I have this graph on the left side, and you can look at the normal values based on your age and based on your height. So if you're for example, if you're 25 and you have a height of for example 152 centimeters, so then this is the optimum, and this is the best point that you should be able to have this ability. Your lungs should be able to breathe out up to this value. That's what it means. So so in this graph you can see the average and the average range, or the normal range that you should be able to achieve if you're at a certain height and at a certain age. Okay, so using your peak flow meter, you see that the picture on the right, you see that this lady is blowing into is a peak flow meter. And how you do this test is that you just need to hold it, just like this lady is holding it, and then you need to inspire as deeply as you can, uh, slowly, or take your time, but you need to inspire deeply and as best as deep as you can, up to the point where you cannot inhale anymore. And then at that point, hold it in, hold it in, and then put that peak flow meter into your mouth, and make sure that your mouth is completely sealing off all holes, so that the air doesn't come out from other ways, from other holes, except going into your peak flow meter. And then you blow into your peak flow meter as hard as you can, to the maximum level that you can. And you're supposed to blow as quickly and as hard as you can, and that will push this, you see this kind of like, you can see there's a level, or uh, there's a thing here that shows you the value of the peak flow meter. So this one will move once you blow into it. So this one will move. So that is the level, that is the value that we take in, and we look at the graph here, and we compare it, right? So this is basically how you do a peak expiratory flow test. And this other test, we call it the spirometry test, is another way of looking at your lung, whether or not your lung is okay and is doing good. You can do these tests, but you need an assistant from, so someone will be telling you what to do, and looking at the values, looking at the chart as you do these tests. So here we have the equipments needed for the test. You need a computer, and you need a device that you can blow into it. And then the principle behind this spirometry test is that as you blow air into this spirometer, then this air will cause the movement of this spirometer, and this pushes the over here there's pen, but actually now it's computerized. Everything is computerized, so that movement or that change is being recorded, and the recorded change is in a form of graph that you can see here on a sheet of paper, right? So, but because now we're not doing it this way anymore, because we have the computer, and everything is digitalized, so everything is on the screen. So you should be able to see this graph coming out at the end of the test. And then this is the graph, if you remember, in the previous slide where we talk about lung volumes and lung capacities, right? So remember this stroke up and down here, this one, this is the tidal volume. Remember that. And then this one that increases and decreases, this is the inspiratory reserve volume, right? So if you don't remember, you can always look back at my previous slide. You can just roll back this video and look back at it. But this is the test that does this, and it will come out and give you this graph that tells you your TV, your IRV, your ERV, and so on and so forth. And you can calculate from your volumes, lung volumes, you can calculate your lung capacities by adding up a few volumes. You get lung capacities. So now we're looking at this spirometry graph, right? So if you have this graph, and then this is this is time in seconds, and you have the volume here on the y-axis, right? So you can calculate in 1 second. So if you put time here, for example, this is 1 second, and then this is, you take this line and you get that. So this is the value of your FEV. This is what people take into account, and this is what people record, this FEV. So FEV stands for the force expiratory volume, and then usually we do FEV in the first second, so we put it FEV1, right? FEV1. So FEV1 is whatever value that you find here at this point. And then you take the maximum level of this at this graph. You can see the maximum level, and for example, is this one. This is maximum level, and you can calculate the FVC, the force vital capacity. So this is what this is all about. And using this graph, we can figure out whether or not the lung is okay or not. And you know that lung disease, there are basically divided into two main lung diseases, and one of them is called restrictive and the other one is called obstructive. And this lung diseases, when you say restrictive, meaning restricting the lungs from expanding, or restricting the lungs compliance to expand, right? The lung compliance. So that's restrictive lung disease. And the other type of lung disease is the obstructive lung disease, where when you say obstructive, meaning it's related to anything that obstructs the airway. So anything that obstructs the airway is categorized into obstructive lung disease. So one of the example of obstructive lung disease is the asthma, because you have this a lot of mucus, and it's terrorizing your airways, and that is obstructing the passageway, the airways, and hence it's called the obstructive lung disease, right? All right, now this is the graph showing you how it looks like in lung disease. So remember, I've talked earlier in the previous slide about we have restrictive lung disease, and we have also obstructive lung disease. And one of these is the graph showing restrictive, and one of these is also a graph of lung with obstructive disease. So if you can guess which of this graph is actually showing which, I hope you can. So this is I'm going to tell you that this curve here is a normal curve. Similarly to this the right one, this curve is a normal curve. It's the normal, showing the normal capacity of the lung, right? So if you look at down here, this abnormal curve showing that there's something wrong with the lung right here. So if you can guess, this person on the left side, or the graph, based on the graph on the left side, you can say that this person is having obstructive lung disease. So I've put an O here, obstructive lung disease, because there's something obstructing the pathway. So you can see that the graph is not a steady curve graph. You can see the dotted line of this graph, it's got some going upward and some going downward. You know, it's not a steady line, right? It's not a steady graph. So there's something obstructing, so you have some of the air coming in and some of the air that cannot pass through this side, maybe it goes this side. So that's why the curve is somewhat you know, up and down. So this is obstructive. And then looking at the graph on the right side, so if you look at the graph on the right side here, so this is the curve that we want to look at, right? So if you look at this curve here, it's a steady curve, right? But it's just you know, less than the curve above, right? So it's less than the curve above. So definitely there's something wrong with this lung as well. And this is an example of a restrictive lung disease, and the curve will come out this way. Why is it restrictive lung disease? Because something that restricts the lung from expanding, and there's nothing obstructing the pathway, the airway. So you have a steady curve compared to when you have obstruction along the way. For example, if you're walking and you have stones along the way, you know, you tend to, you know, sometimes you have to go up and sometimes you have to go down to you know, to prevent from stepping on the stones. But if it's restrictive, for example, you're in a tunnel, for example, and you're not able to stand up, so but because of the tunnel, you're gonna have to bend the whole time, but the bending is at the same level the whole time, so hence you have the steady curve, right? The steady curve, and it's not crooked like the curve you see on the graph on the left side. Okay, so this is the last part of my video. This is to measure the residual volume. And remember, in the earlier slides, I've mentioned that the lung volumes, there are 4. So, and using the previous lung function test, we can figure out the tidal volume, we can figure out the inspiratory reserve volume, and we can also calculate and measure the expiratory reserve volume. But what we cannot measure directly is the residual volume, because the residual volume is involved with measuring the air that's left inside your lung after you maximally force air out, after you maximally exhale air out. So you want to calculate the air that's left inside your lung, which is impossible. So we have this helium dilution test to measure it. This is measuring the volume of air that's left inside indirectly. So by using this formula that we have down here, if you look at it, it's concentration and volume. So the theory behind here is that the concentration and volume, if you times, is equivalent with the concentration and volume after it. So, and you know that after the test, the volume is increases because it's the volume inside the volume of this thing here and this volume, right? So if you can figure out all these values, and you can put it in together, you will be able to find out what is V2, and V2 is the volume that we're looking for, and that is equivalent to the volume of air that's left inside, and that is the residual volume that we're looking for. And this is the end of my video. Thank you for watching, and I'll see you next time. Assalamualaikum and bye bye.